I listened to something. I wasn't you, but then like you didn't have a mask on, so I was like, I don't want to wait because it wasn't you. I was like, okay. Because it was like a 5-second like eye contact. Okay, you have to add me as a
Oh, yeah. So sorry.
All right, welcome everyone. Let's start off with some questions about the homework. So homework 2 is the homework that was due today. Let's see, looking at the statistics. Looks like problem 9 is the one that people took the most attempts on, and that's the one that we talked about yesterday. Are there other problems from homework 2 that people want to talk about? Nope. All right, then let's talk about homework 3. What questions do people want to talk about for homework 3? Sarah. Question 8. Ah, this is chimpanzee named after you. All right. A particular part of this one or just all of it? Okay, so figuring out symbols for the parameter and the statistic. So the parameter is the measurement of either the long run process or the population. So that's what our null hypothesis is about. So that is used, either pi is the one that our book uses, or yesterday we also talked about p as being a symbol that some other people use for the parameter of the long run proportion. H sub 0 is the symbol we use for the null hypothesis. And p hat, because it has a hat on it, the hat generally represents a quantity that's being estimated from a sample. So p hat is actually usually used for the statistic. Does that address your question?
Yeah, thank you.
Cool. Other questions about homework 3? Oh, 9? So the continuation of this? Yeah, so for this one, this is a kind of problem that you might see on quizzes in this class, is giving you a graph from the one proportion applet. So this dot plot was generated by the one proportion applet using probability of heads equal to 0.5, number of tosses equal to 8, and number of repetitions equal to 100. And then we need to figure out from this what the p-value is gonna be. So looking at this scenario, we see that the statistic is that Sarah chose the correct photo in 7 out of 8 scenarios that she was presented. And I think you did this in problem 8. Go back. The alternative hypothesis is that in the long run, this chimpanzee will choose the correct picture more often than would be expected by chance. So we're not interested in the possibility that she's getting it wrong on purpose. So we're only interested in a one-sided hypothesis. Our null hypothesis is that pi or p equals 0.5, and the alternative is that pi is greater than 0.5. So this greater than symbol in the alternative hypothesis tells us the direction that we're interested in for computing the p-value. This says that in our null distribution, things that are going to count as more extreme than 7 or more convincing evidence against the null hypothesis and in favor of the alternative hypothesis is anything 7 or more because of the greater than symbol here. So because of that, we can then go to the dot plot and say what proportion of our simulations were at least as extreme as 7. Well, I'm counting 1, 2 dots exactly at 7. And then 2 more dots at 8, so greater than 7. So in this simulation, there were 4 repetitions that had results at least as extreme as what we observed. And that was out of a total of 100 repetitions. So the p-value then is 4 divided by 100. Questions about that? Other questions about homework 3? Problem 3. Oh, good. So this is a problem that directly relates to the video that you watched before class today. So we have 2 research groups that were testing the same null hypothesis, that pi equals 0.4, but they found different p-values. And we want to figure out which options could explain the difference in p-values. So looking at these 2 p-values, which group found stronger evidence against the null hypothesis? Say what? Group A, yeah. Group A has a smaller p-value. They had stronger evidence. So we need to look at each of these options and decide whether it's a good explanation for why group A would have stronger evidence against the null hypothesis in favor of the alternative hypothesis. So option A, group A had a prior reason to believe that the proportion was not less than 0.4. So that would correspond to group A was testing null hypothesis that pi was 0.4, and alternative hypothesis that pi is greater than 0.4. And then implicitly, if we suppose that group B did not have that same prior reason, their null hypothesis would be the same, but their alternative hypothesis would be a 2-sided alternative hypothesis. That pi was not equal to 0.4. So how does the type of alternative hypothesis affect the p-value?
The one portion afterwards stronger evidence or 2-sided.
Yeah, with a 1-sided alternative hypothesis, you tend to get stronger evidence than with a 2-sided. And specifically, typically the p-value for a 1-sided test is going to be about half of the p-value for a 2-sided test. And that looks pretty reasonable for what we got here. That group A's p-value is roughly half of group B's p-value. So that could be the reason why, is that if group A had prior reason to believe the proportion was not less than 0.4. No.
If I'm lying, I would just get mixed up if a smaller or a larger value is stronger evidence, and like how that relates to like the A and B, the two-sided or one-sided is stronger evidence.
Yeah, so I like to come back to what we talked about sort of on the second day of class of thinking about the p-value as being a measure of how far in the tail a result is. So if we think about this as being our null distribution, so the dot plot that you get in the applet of what results you would expect if the chance model was true. And like, let's say here is our result from our data. That's our sample proportion p hat. The p-value is telling us how much probability is in the tail here. So how extreme is this p hat? So the smaller that is, the stronger the evidence. That in the strongest case, like the activity we did yesterday, you might see here's the null distribution, what we expect if the chance model is true. And then way out here is p hat. So a situation where we never observe this p hat if the chance model is true. That would be a p-value of approximately 0. Or you could say the p-value is less than 1 out of the number of repetitions that you did in your simulations in the applet. And this would be very, very strong evidence that the chance model is not what's going on. So to be very strong evidence against the null hypothesis. And then, so the difference between a one-sided and a two-sided alternative hypothesis is that what I've just drawn here would be the p-value for a one-sided hypothesis, where we're only looking at the tail that's on the same side as the p hat. For a two-sided alternative hypothesis, we'd also look on the other side of the center and find that probability as well. So that's why the p-value for a two-sided alternative hypothesis is usually about twice as big as the p-value for a one-sided alternative hypothesis. So when we're doing a p-value for a two-sided alternative hypothesis, we start by finding this probability of being greater than or equal to p hat, say. But then we also go and find sort of the equivalent point on the other side of the center of the null distribution and find the probability of being less than or equal to that. So that's why the p-value for a two-sided alternative hypothesis often ends up being about twice as big as the p-value for a one-sided alternative hypothesis. Because you're basically finding the probability of about twice the area. Okay.
Could you give another example of a two-sided, whatever it was?
A two-sided alternative hypothesis? Yeah. Like a research question where that would be what we'd be interested in? Yeah, so the two-sided alternative hypothesis is a good default when you don't have any prior reason to think that this thing has increased or this thing has decreased, just that it might have changed. So for example, I wonder if COVID has changed the proportion of UWEC students who want to be nursing majors. And maybe it's increased it because it's this like real world, really important thing that they want to go into nursing so that they can help people with COVID. Or maybe it's decreased it because, oh my gosh, that's so much work. And if I'm going to nursing, then I'm going to be on the front lines and exposing myself to disease, and that I don't want to do that. So there's sort of a reason to think why it would be interesting to see if it's changed. But I don't really know to expect whether it to be bigger or smaller than it used to be. So in that case, I might set up my hypotheses as a null hypothesis that pi is equal to some number, so whatever the proportion from before COVID. So the null hypothesis is that nothing has changed, it's just stayed the same, and if I happen to get a sample with a different proportion, then that's just because of random chance in who I sample. And then my alternative hypothesis would be that pi is not equal to that same number. Does that answer your question? Cool. Let's talk about these other two options in this problem. So option B, group A found a sample proportion of 0.5. Group B found a sample proportion of 0.35. So this option is getting at the issue of the distance between the sample proportion and what you hypothesized in the null hypothesis. So the null hypothesis was that pi equaled 0.4. Group A found a sample proportion of 0.5, and group B found a sample proportion of 0.35. And let's go ahead and assume that both of these groups now are using a two-sided alternative hypothesis. So here, group A's distance between the hypothesized value from the null hypothesis and what they got in the data, their sample proportion, is 0.5 minus 0.4, so 0.1. Group B had a distance of 0.4 minus 0.35, so 0.05. Based on this, which group would you expect to have stronger evidence against the null hypothesis? Right. Yeah, the bigger the difference, the stronger the evidence. So we would expect group A to have stronger evidence, and that agrees with what we saw. So option B is also a valid possible reason for what we're seeing in these p-values. And then option C, group A used a smaller sample size. So assume that everything else is the same. So they're both using a two-sided alternative hypothesis. Forget about the possible difference between their sample proportions. if the only difference between the two groups is their sample size, and group A had a smaller sample size, which group do you expect to have stronger evidence against the null hypothesis? Right? So if group A has a smaller sample size, okay. Brady, did you start to raise your hand?
No, but
It's group B. So the more data you have, the more evidence you're going to have to be able to detect a difference if there is one. So for example, if I want to know whether the proportion of UWC students who are nursing majors has changed, I could survey 10 students, but that would give me a pretty coarse estimate of what proportion of students are nursing majors. Or I could sample 10,000 students, like almost all of the school. And then I would know really precisely what proportion of students are nursing majors. So the stronger evidence comes from that larger sample size that gives us more information to sort of narrow in on what exactly is that proportion. So option C is not a good explanation. If option C were the case, then we would expect group A to have a larger p-value than group B, because group A would have less evidence. Questions about that? Here.
Doesn't a smaller sample size result in more extreme differences? From smaller sample size, we probably wouldn't fall right in the middle, so it would be the whole equation where you use large sample.
So it is true that with a smaller sample size, like you're going to get coarser estimates. So like with a sample size of 10, I'm either going to get like 0.3 or 0.4. I'm not going to get 0.328, which I could get if I had a sample size of 10,000. But with a smaller sample size, if the null hypothesis is true, your null distribution is still going to be centered around whatever that value from the null hypothesis is. And any difference from that, that's due to the fact that your sample size is small, is sort of going to be baked into the null hypothesis, the null distribution. Let me see if I can illustrate this.
Actually, did it.
Okay.
It just clicked in my head.
Okay. Other questions about this? All right. First of all, an announcement, which is that if you've been looking at the course schedule or on your assignments on Canvas, you may have noticed that there is a quiz and a practice quiz up there. And I originally set quiz 1 to start today and be due before the start of class on Monday. But I totally failed to tell you about that on either Wednesday or Thursday. So I apologize for that. So I'm telling you about it now. There's a practice quiz available that I think is a pretty fair representation of what's going to be on the actual quiz. And I'm going to extend quiz 1 so that it will be due before class on Wednesday of next week instead. So you can take it over the weekend if you want. Remember, I do have office hours on Saturday, so feel free to stop by those if you have questions about the practice quiz. Or if you want to wait until my office hours on Monday or to send me an email on Monday, you can do that so that you can get your questions answered before the quiz. Sound good? All right. And then let's debrief about our Gallup poll activity from last time. So this was a hard one because we're sort of making a leap from talking about an infinite process where the value from the null hypothesis is sort of inherent in the setup of it's like, oh, the dolphin either gets it right or they don't. So its null hypothesis is pi equals 0.5. Here, it's a little bit more complicated because we're dealing with two different years. We've got the setup from 2005, and we want to test whether 2016 is different, whether things have changed compared to 2005. So what do we want to have for our null hypothesis in part one? Let's do it in symbols first. Right? Yeah, 0.35. So we're getting that value from the state of things in 2005. So we want to test whether 2016 is different. And in order to do that, we're saying, suppose that it's not different. Suppose that what happened was the exact same percentage from 2005 is still true in 2016. In that case, then 35% of people being in favor of legalizing marijuana is the chance model, meaning that any difference in our sample of, maybe in our sample, 38% of people were in favor of legalizing marijuana. But that, under the chance model, that difference between 35 and 38 would only be due to chance in who we happen to survey. That really, if we could survey everybody in the US, the percentage would be 35%. And we just happen to randomly get a sample that was slightly more than 35%. In order to phrase this in words, something to point out here, something that people often have trouble with when they're getting started with writing hypotheses. You sort of set it up as H sub 0 colon, like here comes the null hypothesis. And then you write pi equals whatever. So the equal sign is coming between the parameter, so pi or p, and the value that we're saying that that's equal to in the null model. Okay, so in words, we want to basically describe in words what this parameter pi represents. So often, pi is the long run proportion that whatever. In this case, because we're dealing with two different years, I think the words long run are actually kind of confusing. So I think it's a little bit clearer to say the proportion of all US adults in the population in 2016 who are in favor of legalizing marijuana. Is 0.35. So I've highlighted some keywords here. The words all and in the population are there to remind ourselves and our readers that this pi, this parameter that we're talking about, is a parameter. That it's not just about this one sample that we took, it's about the whole population. And then the in 2016 is sort of a keyword for this problem to help us distinguish between the 2 years. So in 2005, 35% of US adults were in favor of legalizing marijuana. That's where we got the 0.35 here. But that's not actually the population that we're studying. If you scroll down, the survey that we're analyzing here was taken in 2016. And the parameter is always about the population that the sample was taken from. So in this case, our sample was taken from adults in the US in 2016. So that's what our null hypothesis is going to be about. Questions about this? All right. So then for our alternative hypothesis, we start with H sub A colon, and then we're using the same parameter, so pi, and the same hypothesized value from the null hypothesis of 0.35. The only thing that's going to change is the symbol that goes between them. So what symbol should we use for this study? Yeah, why is it greater than?
Because we expect that it's going to be just having more people supporting the legalization of marijuana than there was in 2005.
Yeah, that's the research question that the researchers were interested in.
So, does it matter if you put like greater than or equal to sign? Because isn't that the only option on that one question output? Is to do like n equal?
Good question. So for the alternative hypothesis, you don't want greater than or equal to, because you don't want the alternative and null hypotheses to overlap. You want them to be completely different possibilities. But you're right that that is a little bit different from what the one proportion applet shows us. So let's see, proportion of successes. If this is our null distribution, so what we expect if the chance model is true, and we want to compute the p-value, we're putting in our observed statistic into this box. And then it gives us the options of as extreme as greater than or equal to or less than or equal to. The reason the equal sign shows up there is because the p-value is the proportion of simulations that are at least as extreme as what we observed in the data, not just more extreme. than what we observed in the data. Does that make sense? All right, and then for writing the alternative hypothesis in words, I'm going to change greater than, but we can leave sort of the rest of the sentence the same. The proportion of all US adults in the population in 2016 were in favor of legalizing marijuana. All right. So then we come to doing this in the one proportion applet. So the probability of success or probability of heads is the value from our null hypothesis. So that's going to be 0.35. And our sample size is the sample size in the study. So in this study, it was a sample size of 1,017. And then if I want to compute the p-value, what number should I put in this box? Nettie? What's that? 0.35? Let's find out what happens if we do that. And then which direction do we want this greater than, less than sign? Greater than, because we want that to be matching the direction of the alternative hypothesis. So because the alternative hypothesis was greater than, we want to count samples that were as extreme as greater than or equal to something. So in that case, we get a p-value of 0.537. What do people think about that? Allison, you're shaking your head. What did you have in that box?
I don't remember what we did. We didn't do that.
All right. Mary? Yeah, why is it 0.6?
Because that was the result from the survey. We want to see if that's like a random occurrence or if it's like
Exactly. So our result from the survey was that 60% were in favor. And we want to find out if that was a random occurrence, something that could occur just by chance in who we sample. So that gets us a really extreme result. That out of these 1,000 repetitions that I did, none of them had 60% or more people in favor of legalizing marijuana. So we would say that the p-value is approximately 0, or that the p-value is less than 1 over the number of repetitions or simulations that I did. So I did 1,000, so I would say it's less than 1 out of 1,000. Because that's saying I did 1,000 repetitions and not even one of them was at least as extreme as what I observed in the data. So how would we interpret this p-value? Mary, go ahead.
Assuming that this survey was done in the same population that included 35% of 2005, it is extremely unlikely that the 60% support legalization of marijuana occurred.
Very nice. Anyone else have a different way of phrasing it? So where does less than 1 out of 1,000 fall in our table of strength of evidence? Mackenzie. Very strong, yeah. So there is very strong evidence that, and then we can start, oh, sorry.
I was gonna ask if you could say like, there's some evidence against the null hypothesis.
Yeah, so we can say there's very strong evidence against the null hypothesis. If the question asks you to interpret the p-value in the context of the study, then you would want to take that a step further and say what the alternative hypothesis was, like in words from the study. So in this case, we could say there's very strong evidence that the proportion of US adults who are in favor of legalizing marijuana is greater than 0.35. I should get the year in here somewhere, US adults in 2016. Or we could say there's very strong evidence that the proportion of US adults who are in favor of legalizing marijuana increased from 2005 to 2016. Right.
So when you said interpret in the context of the study, did you mean that we're supposed to add the null hypothesis, or we're supposed to include the alternative?
So personally, I think it's easiest to say there is very strong evidence that alternative hypothesis. It would also be true to say there's very strong evidence that not null hypothesis, but then you have a not in there and it's just more complicated. Questions so far? All right, so we sort of phrased this conclusion in terms of all US adults in 2016. What more would you want to know before really saying, yeah, all US adults in 2016, as opposed to just some population represented by this? What more would you want to know before you generalize these results? The age range, so was the sample taken from the range of all US adults, or did they just survey people, I don't know, between 25 and 40 or something? Yeah, what else? Okay. Location, yeah, so if they just did the survey in Wisconsin, then those results might not generalize to other states. Other thoughts? Any?
It's kind of like location, but like if it's people who live in urban.
Yeah, so did the survey sample fairly from people who live in urban versus rural locations? And that doesn't necessarily mean that the percentages have to match exactly, like exactly the same percentage in the sample live in urban locations as in the whole population of the US. But you want to make sure that people who live in a particular location weren't unfairly underrepresented or overrepresented. Yeah. So if people of a particular income range are more or less likely to be in favor of legalizing marijuana, you wouldn't want that to bias the results. So we don't have the statistics about each of those sort of subcategories of factors that might make the sample representative or not. But here's what we do know. So the study was conducted by the Gallup Poll company, which is a well-known company that's quite experienced in conducting surveys. They used random digit dialing to survey people with landlines and cell phones. So they dialed digits randomly. So hopefully that should get a relatively fair cross-section of people with telephone numbers. It might slightly bias the results to people who have more than one telephone number. And it's probably going to somewhat underrepresent people who are homeless, who might not have a fixed phone number that they can use. So maybe we should say that our population was all US adults in 2016 with phones. They did survey people in all 50 states, and they gave people the option to complete the survey in either English or Spanish. So not other languages. So this might be underrepresenting the opinions of people who don't speak either English or Spanish fluently enough to have a phone conversation. But let's look at specifically this issue of population size. So the population size of the US is about 319 million. Should we be concerned that this survey only included 1,017 people? What do you think? Think about it for a minute. Let's do thumbs up for yes, I'm concerned, thumbs down for no, that's not something I'm concerned about. See a lot of thumbs up. I would actually say thumbs down. I'm not particularly concerned about the sample size here. I think that a sample of size 1,000-ish is going to be enough to get people from all 50 states and from a wide range of ages and income brackets and sort of other demographics. So once we've established that it's sort of reasonable to cover a range of possible values that might influence people's opinions about legalizing marijuana, having a larger sample is nice because it lets you get stronger evidence against the null hypothesis, if there's really a change there to detect. But we already saw that our sample of 1,000 gave us super duper strong evidence. We got a p-value of approximately 0. Having a larger sample size in and of itself would not make this sample more representative. the things that make the sample representative or not are these issues of, okay, they surveyed a good cross-section of people with phones. They surveyed people in all 50 states. They surveyed people who speak English or Spanish. If we want to make our sample more representative, we need to look at those issues. Let's get some translators who speak Hmong and Arabic. Let's figure out a better way to survey homeless people who don't have phones, things like that. The fact that the sample size is small compared to the population size is not really a concern. Questions about this? Jake.
So let's just say the US population, say it's 2 billion. Would 1,000 still be fine with that?
Yeah,
If it's still
so
50 states and everything else the same other than versus more people.
yeah, so the population size is actually not that relevant. So if the population size was 2 billion or 2 million, the 1,000 people is still approximately equally representative based on these other factors. It doesn't matter what the ratio of those two sizes is.
So it's 4,000 like in general number of
That's a good question. No, I would say often you can get good results with a sample size of a few hundred. I think 1,000 is something that the Gallup Poll often uses because they're trying to survey people from all 50 states. So they want to make sure they get some people from all those states. Beyond that, people will often choose a sample size based on how likely they want to be to get a small p-value if the difference between the null hypothesis and what they get in the sample is a particular size. So that's called a power calculation, and we'll talk more about that later in this lesson. Sandra. From Jeopardy?
No,
Family Feud? That's a good question. I don't know.
So I always like, I see someone else, I'm like, who are they? What are they?
Yep, I don't know. All right, so thank you all for your attention. I will see you on Monday.
Yeah.